Good morning, class, and welcome to week 8 in Physics 101. Today we're dealing actually with the concept of energy. I know we did a lab for it last time, but we're going to delve in it a little bit more in detail. It's the same things that we did in the lab in terms of concepts, basically the energy in general, and we're going to break it down into two forms of energy. We're going to deal with the kinetic energy, namely the energy of motion, and also we're going to deal with the potential energy, which is really an energy of position. Okay, if an object has, for example, for the case of gravitational potential energy, has a certain height with respect to a certain reference frame. So in this case, I would say that it has a potential energy. How do I know that? Just if I let go of it, it's going to convert it to another form of energy, which is one of the properties of the energy, that the energy is, it transforms from one form to the other. Then there are all the kinds of energies that we really are not going to delve with them. And there are also energy of potential energies that is namely the electrostatic or electrical potential energy, and there is also the magnetic potential energy, and both of them are actually the same, one form of another. So they're called actually electromagnetic energy in this case. There is a nuclear energy, which I don't think that we will have time to, or it's not included in this class. And that is basically the different forms of energy, the fundamental forms of energy. However, energy involves also another kind of interactions, namely work. For example, there are forces that do work, but they don't necessarily are associated with any kind of energy. Case in point, for example, energy is associated with losses, like, for example, friction. Okay. Those are energies that are actually a result from, or actually work that takes care of taking one energy and changing it to another form of energy, like thermal energy, heat, namely. There are other forms of energy that we're not going to delve into, but I mean, let's say, for example, and since I already mentioned the fact that there are gravitational potential energy, electromagnetic energy, and also the fact nuclear energy, but where is, for example, friction fits in? Friction is actually another kind of electromagnetic energy because it involves the interaction of different surfaces or materials, and that involves the charges, the outer charges in them. So this is basically, in a nutshell, what this topics are. And then the rate at which energy is being dissipated, or at least the rate at which work is being done, that is actually called the power. Okay. So these are the concepts of today. However, the lab today is going to focus on electricity and magnetism, namely electrical interactions. Two charges of a similar type will repel, two charges of a different type will attract. And we're going to basically explore this one and the effects also of distance. So as the distance gets further and further away, the charges are less and less attracting one another if they are of different kinds, or less and less repelling one another if they're of the same kind. So distance also have an influence, and as a matter of fact, the distance squared. So this is what the lab today will explore. There are important stuff that is actually related to today, so I want to really also throw it out there today, because if you guys have had a chance to look, let me share the screen. If you have had a chance to look at the modules this week, the model for this week, namely week 8, of course, we're exploring the concept of energy and electricity. The objectives in here. And there is a quiz, which is actually 3 videos, all combined are less than 20 minutes. Okay, so they're like 17 minutes, I mean, all 3 videos. So hopefully you guys go through them. There is a discussion item in here, which is important that you understand what I'm trying to argue in here. There is a word conservation of energy, which is part of this chapter that we're going to delve into. And you hear also all kinds of talk about conserving energy, conservation of energy in society in general, whether with politicians, activists, news reporters, and a lot of people talk about the conservation of energy and the need for conserving energy. That is basically, that is a question that is out there. Now, in terms of physics, this is a no debate. This is already a fact. If a system is closed, the energy is conserved. The energy is not increasing somehow. It's not, you're not going to gain energy. You're not going to lose energy if the system is closed. So the question in terms of physics is really conceptually, it's a done deal. However, in society, they have a different lead for it because of the fact that there are limited resources for our energy use, like, for example, hydrocarbons and for oil, for example, or for nuclear energy that has all kinds of environmental issues. So in terms of this point in here, yes, there is the carbon footprint, which is also associated with how much we're causing basically the planet to release more carbon, which will go and increase actually the amount in the atmosphere, which will later on affects the greenhouse effects on Earth and increases the temperature overall. So there is this debate about the environment, and I want you guys to make the distinction between the two. So I want you to research basically the topic out there. The physics part of it, namely chapter 7, is clear cut. There is no debate about it. So you should be able to compare the two and what is needed in there. So that's really the discussion item in here. The lab is here, and this is actually why I'm here today. It's because of this exam review. The exam review, you have about, I mean, how many days? It's not going to be available today. It's going to be available on Wednesday, but it's not due until not next week. So you'll have a week and another week. So the exam is actually due on November 9th. That's when the date of the exam is. That is when we're not going to have a live session, on November 9th. And it's going to include the chapters 2, 3, 4, 5, 6, and 7. So these are the chapters, 6 chapters, because chapter 1 was included with the first exam. Chapter 1 and other chapters from on sound and waves, the mid-teens and toward the end of the teens. So those were included in exam 1. Exam 2 only covers chapter 2. All mechanics basically is included. Chapter, this one in here, which is going to be due this week also, namely chapter 20, where we jump into electricity and magnetism, is not included in exam 2. So that you guys have this distinction. And so that's why I brought you guys in here. There is a lot of items in here that needs to be covered. So I want you guys to go thoroughly about it, okay, in your preparation. However, and a big however, this only review covers the conceptual components of the exam, namely the related topics in terms of concepts. There is another component for the exam too, namely the problem session of it. And we did a discussion on Wednesday, October, Monday, not the 17th, but the 10th. We went thoroughly on several problems in there. We discussed them. And also last week, in lab, we also went through other examples from the homework assignments. If you notice, there is no homework assignment this week because you have plenty up to this point in here and that are due. One of them is November 5th, which is the weekend before the actual exam. So this is just a heads up start on this review. I know the review is not going to be available for you until Wednesday, but you still have 2 weeks to plan for it. So I want you really to guys to make sure. The reason why I wouldn't make it available today is because of the fact we still have the energy to cover, okay? I hope this makes sense to you guys. I hope that you guys will have plenty of time to prepare for your exam, both the conceptual and also the problem version of it. And we would not have any difficulties. And if you guys have any issues related to the review or the homework assignments or the math, the problem section of it, please let me know, reach out. You have plenty of time. You have more than 2 weeks for the exam. So we should really hammer down all of these things. Another point in here that you should have received an announcement on it already from Canvas, and in order to help me actually and help the college, there is a survey out there. Please fill it out as soon as you can to make sure that the information is received. The due date for that is November 16th. So, and I already sent you a message regarding that, okay? So this is in terms of all of the stuff that needed to be said. The lecture today is going to be light in a sense because a lot of these things we discussed them in lab. Actually, we did a full lab on it. So let me go through the notes and see if we can go sail through this thing quickly. So let me jump into the chapter 7. Okay. So the concept we're going to be dealing with today is concept of energy. Honestly, the book delves into a lot of questions about the mysticism, if you wish, associated with energy, and that is really not healthy. So don't waste too much time on those things, okay? They are not relevant in terms of concept, okay? So energy, like any concept in physics, if you can measure it, it's a physical concept. If you can devise a measurement that satisfies all the requirements for physical science, you're in good shape. So if you wish, let me restate the question here in a different fashion and how the energy arose to begin with. Okay, how the energy came about, the concept of energy. It's not like somebody was sitting in his room, basically, minding his own business, and then boom, it hits him and says, okay, today I'm gonna define energy as being 1/2 mass times velocity squared for an object moving with a velocity v and with a given mass m. No, it did not work that way. There is a rationale behind it, and I'll explain what that rationale is. We know F equals to ma. That was a law that Mr. Newton has postulated, and that's a law that is proven by everyday experience. So every day you take an object of a given mass and you subject it to a force F. The result is, so you know how much force you put in, you know how much mass it has. You go and see what happened to the object. It's going to accelerate, it's going to move. Whatever velocity it had, it's going to increase in the direction of the force by an amount that is, you can measure also in the lab. You check the value that you measured for the acceleration, you know the value of the mass, you know the value of the force, and then you divide the force by the mass, and it is the same thing as what you measured for the acceleration. Checked. So the law of Newton, the second law of Newton, is a fact, and that's why it's a law, okay? Then people started to think about, how does the force do it? How does the force change motion? Because that's exactly what the second law says. If you take an object sitting at a given point, okay, and you apply force to it, obviously that object will change motion. Okay, that's what the second law says. And you wait later, and you see the object has moved to this point. It was here, now it's here. You would want to compare the initial and the final positions, that's all. What has changed from initially to finally? The object had a position to begin with. The object with a certain time has a position in there. The object has a different position in here. But the object could potentially be in a different position. So the position really is not the issue, it's the velocity. Okay. If you work out that F equals to ma, mathematically, you're going to say it's equivalent to something that happened, that the force will do work in such a way that that work is a change in a quantity, which is 1/2 times mass times velocity squared, which we later on denoted as kinetic energy. That's basically what happened. And I'm referring to this expression. I know it's in your summary also on Canvas. I posted for you in terms of concepts. So I'm looking for it in here. It's in the notes. Actually, it's in the book also. The book goes through it in detail. Here is the expression I'm looking for. This one. W equals to delta KE. So this is the one that defines actually the kinetic energy being 1/2 mass times velocity squared. So you take a force, you allow it to do its trick, to take an object from a given point, and the object will go through a path. It doesn't matter which path it does go through. And then it reaches the second point, and you decide to compare the 2 points. When you compare them, you find the increments in work, which is force times displacement, that goes from place to place to place to place to place to place. That's what work is, okay? Until you find the total amount of work, and you compare it to an initial value, which happened to be 1/2 times the mass times velocity squared. It really emerges from something called calculus, which is another concept in math. Then that value changes from an initial value to a final value. It doesn't matter what the intermediate, what in between is. What matters is the final value and the initial value, period. 1/2 of times the mass of the object times its velocity squared at the end, minus 1/2 times the mass of the object times its velocity from the beginning, and that's the end of it. There is no mysticism in here. There is no kind of a magic in here. All the magic, if you wish, is actually in the details of how to find the work. The work is force times displacement, and it's actually defined in here somewhere. Here, the work is force times displacement. So the force is the one that is doing work. The force times how much the object has moved, and you add up the quantity. Okay, in calculus that's called integration. But you don't really need calculus to do this. All you have to do is just define the distance, so the distance times force. That's it. Okay, you don't need fancy tools in math and big words and things like that. Force times displacement, and as the object moves, you add up this quantity, and that's the end of it. So that's his work. So on one side, force works. On the other side, the quantity that keep on changing because of that work is always 1/2 times mass times velocity squared, which we later on gave it a name, and that is basically the kinetic energy. Because why we call it kinetic energy? Because it's an energy that is associated with the velocity. Remember, motion is velocity. An object that does not have velocity is not moving. An object that has velocity is moving. So whatever initial velocity was and whatever final velocity is, this quantity matters. Obviously, the mass in here enters because we're dealing with an object, and the force is at the end is really moving that object. And if you're wondering about this 1/2, where it came from, again, it's a calculus requirement. Okay. Historically, this concept was explored by I forget her name. It's okay. No. I'll try to remember it later on, okay? Man. Okay, let me try to find it, okay? We'll actually Google it, okay? Oh man, I forgot her name right now. I'm trying to think, and I forgot the name of the lady. It was in. She's actually she befriended Voltaire, and okay, Emily du Châtelet. That's what I did actually. I just Googled. Let me share with you guys her name. And actually, there's a picture of her too. It's not a. So Emily du Châtelet, that's actually a rendition, a movie of her story, basically. She was a French, basically. She was a very young woman and married to a wealthy person. At the end, she befriended Voltaire, who published her work, but under his name. Okay, that's basically something that. So basically, what the idea was at that point, people were exploring how mass and velocity combine to impact other objects, okay? So what they thought about, at least in the English-speaking world, she was from France, is that, and also the German region, is that, look, if I take an object and give it a mass, its mass times velocity is the one that is going to create an indentation in, let's say, clay, for example. But she proved beyond the shadow of the doubt that it's not actually the velocity that that matter is square of the velocity. Because if you take clay, for example, and you drop an object from a certain height, it's going to gain a velocity and it's going to create an indentation. And no problem about it. That is the concept of oomph that was discussed by the English people at that time, England and Germany. But what she did was she doubled the velocity. In other words, dropped it from a different height in such a way the velocity is twice of what it was before. And she noted that the indentation now in the clay is 4 times as it was from the initial velocity. So suggesting now as the velocity doubles, the effects of this oomph quadruples. If you triple the velocity, she saw that the depth is 9 times as much as it was before. So the indentation in this case is relative to the square of the velocity. But that's how the concept basically laid at the end. It was Mr. I think Young is at the end used the word energy for the first time for that, okay? Energy of motion. The point being in here is that is mv squared where it was coming from. In order to reconcile the two, namely the work that Miss Emily du Châtelet basically has discovered, and Newton's second law of motion, which she actually translated all of his work to French. And at the, as I was saying, it's actually what's his name, Voltaire at the end, who published her work under his name. So that's something that is kind of not fair. And she was not happy with it, of course, but she was a woman and there was a lot of discrimination at that times, and women were not respected and thought of as being basically smart enough for basically capable of doing what men can do. So that's part of there's a lot of bias, in other words, in those times. And that's why you saw a lot of movies on her and things like that. Anyway, the point being in here is the 1/2 was added later on to reconcile F equals to ma with this portion in here, which is 1/2 of mv squared. Because if you take the derivative, that's another concept from calculus again, of 1/2 of mv squared, you're going to fall exactly back to F equals to ma. So in other words, this answers the question. What happened? How does the force do it? Well, the force works to change the kinetic energy. End of the story, which is this theorem, which is this relationship. The delta in here means change. So the force works to change the kinetic energy. That is basically, in a nutshell, what the whole point is. Then the force is ma, mass times acceleration, and the displacement now, whatever that is, and you can do the algebra and everything fits and beautifully and everything else. This relationship in here is very, very, very important. Work equals to the change in the kinetic energy. It is important to the point that it really is independent of F equals to ma at all, and it can be extended to other fields outside of the classical mechanics. So it's really, really a big deal. And it is equivalent to the second law of Newton. In other words, if we were to say, for example, I don't know Newton's second law of motion. I don't know F equals to ma. Can you show me that is true? Then you tell them that by experiment, I can prove that the work of a force changes the kinetic energy. And if that's the case, I can prove Newton's second law in classical mechanics. So in other words, your starting point for making a sense of the word is either Newton's laws of motion or the so-called work energy theorem. Work energy theorem. So one of the two can be your starting point, and the other one will be the consequence of that. So this is why it's really a crucial point in here in our discussions in here for this point in here. So I just want to bring your attention to this concept. I know we did them in the lab, but we did not really delve into them too much in terms of the background and things like that. Like I said, the book really gets into a little bit of detail, especially bringing Mr. Feynman in the discussion. Mr. Feynman was he was a Nobel Prize winner in physics, and he was one of the best teachers of physics. And of course, he tries to give you the insights of things. And this is basically, in a nutshell, what he says. there is a quantity out there, mathematical quantity in there, which is the energy. Excuse me, if we compute it before and we compute it at the end, no matter which process the system goes at the end, this quantity is conserved. You have to take these words in a more general sense than what we're doing it in our class. We talked so far about the kinetic energy. I did not talk about the potential energy. If you add the kinetic energy plus the potential energy, plus any other forms of energy, namely energy associated with waves. For example, if two things happen, they touch one another, they may produce sound, which is a wave. And that is actually for another form of energy, it takes with it energy and dissipates energy in the form of sound. There is heat, actually, which is another form of dissipation. There is all kinds of like chemical energy in this case that is involved. The fact that I am pushing one hand against the other hand, that is actually a chemical energy coming from the muscles, basically, that are pushing on one another. So there is another form of energy that is out there, chemical energy and heat and friction. All of this are parts of another form, basically electromagnetic energy. So they're of that form too, including sound. What sound is moving the molecules basically in the air until they come in here and yank your ear, which is a combination of a mechanical energy because of this motion, and also the fact that there is interactions between the charges and repulsions and expulsions, and repulsion and traction. So that is basically all kinds of forms of energy that you can break them down in their fundamental forms. The point being in here, if you take all of these things combined before and all of these things combined at the end, then that's quantity that is conserved. It doesn't change no matter what. Whether you're for it or against it, it doesn't matter. Whether you're for conservation of energy or against conservation of energy, despite of your choices, is going to be conserved, okay? But this is actually from a fundamental point of view. As I was saying in the discussion this week, there might be articles out there that you're going to find, or postings or YouTube postings and things like that about the conservation of energy and the need for it. And that has to do with the environmental issues. That's what Mr. Feynman was talking about. Now, in order to make the problem easier for us, what we usually do is we isolate the system. And we think of it as closed system. And then it's easier for us to track. Again, in physics, usually we don't tackle everything at once because we don't know how. So what we usually do is we break things into smaller and smaller components until we have them under control so that we can control them. And in that situation, we can simplify the problem a lot easier than what it was. The kinetic energy, there is no avoiding it. So the kinetic energy, the fact that it's 1/2 times mass times velocity squared, this is a quantity that is not going to be avoided. As long as you have velocity for an object, it has kinetic energy. This is the energy of motion. Now, another form of energy that is easier to deal with is the gravitational potential energy. If I take an object sitting, for example, at rest, it's not going to move, okay, at least from here, unless I give it a certain height. If I let go of it, then it's going to change to a form of energy that I know of, namely kinetic energy. So where did it get that kinetic energy to begin with? Now it doesn't have any kinetic energy. Now it does. So at some point it did not have any. So in the beginning, before I let go of this, it has no kinetic energy whatsoever. It's not moving. If I drop it, it gained kinetic energy, and now I can find 1/2 of mv squared for that object. So I asked, where did that energy come from? Since I know energy transforms, it came from the fact that the Earth is pulling on it. So if I calculate the work in this case of the force of gravity, I will see that the force of gravity has a certain value in here. Its potential energy has a certain value in here, and it has a different value in below. Since it's a higher point, it had a higher potential energy than at this point. What matters really is the difference in potential energy, not the potential energy per itself. So what matters for the gravitational potential energy and any potential energy in general is not the value at that specific point. What matters is how different is it from the initial and the final. That's basically in a nutshell what that is. Okay, so we're going to come to the collisions in here because it's an important example that we need to discuss too. I know we discussed it when we did the collisions, when we did the momentum, but it's an important point to explore it in terms of the energy. What is the potential energy here? Gravitational potential energy. So again, the form for it mathematically is mass times g. That g is the same thing, that 9.8 meters per second squared, okay, times how high is the object from a standard point. So you're asking how high. Where would I put the height? Am I going to put it from, because if I'm going to take a ruler and start measuring, am I going to measure it from the ground? Or am I going to measure it from the desk? Or am I going to measure it from my hand? So it matters where you start the point. What I'm saying in here, it doesn't matter. What matters is, so you can start from the ground if you will, you can start from the desk, you can start from your palm in this case, and measure this distance only. It's going to yield the same value. Why? Because what matters is that the height that it actually fell, that's it. So if you're measuring this one in here from the ground, you have to measure the final from the ground also and take the difference. So at the end of the day, what matters is just the height from the initial to the final, end of the story. So those two forms of energy that we know of. So if the system is isolated in a sense that these are the only two things interacting, namely the air also is not there because the air will play a role in slowing down this object. So there is no air. Or if it is, it's so negligible that it's not going to contribute anything, okay? There is no, for example, sparks of kind of discharges, electrical discharges somewhere. So there is nothing in there. There are no magnets. If this one is, for example, made out of iron, I could put an iron, for example, a magnet on top of it, and it's not going to fall. So it's not going to give me 1/2 of mv squared plus mgh equal to a constant. In other words, if all of the other things do not exist, with the exception that we have Earth in an object at a given height, then in this case, add this number, mass times g, which is 9.8 times height, to this number, 1/2 of mass times velocity squared of the object, and compute it in the beginning. Let's say, for example, you find 10 joules. For example, you find 10 joules. Compute it at the end when it reaches the ground. You're not going to find anything more or less than what you started with. You're going to find exactly 10 joules. That is what we're saying in here, that the energy is conserved. The energy in the beginning and the energy at the end add up. I mean, the total energy. I don't mean the kinetic energy or the potential energy. So when you add them up, at the end, you're going to find the same number when you start with and the same number when you end up with. So this is what we call conservation of energy. If the system is closed, no matter what happens in between, the total energy, which is the sum of kinetic plus potential, is the same, at least for the force of gravity. This is true also for the other forms of energy too. If the system is isolated, the total mechanical energy is the same from the beginning to the end when you add them up. I mean, when you add up kinetic plus potential, it's going to give you the so-called mechanical energy, total energy. So what happened in here? The object has no kinetic energy, but obviously has a potential energy. So all the numbers for the total energy is just potential. Why? Potential plus 0 is going to be total mechanical energy. So that means all the energy is actually potential. When I drop it before it reaches the ground, before it reaches the lowest point in this case, it lost all of that potential energy and now it has 0 potential energy. And all of that potential energy now is converted to kinetic energy. So if you go on a roller coaster, for example, can I draw in here? I guess I'll try. So if you go on a roller coaster, for example, and you come from this height, from rest, okay? As you go down, at that point, that's your total energy. E, which is the sum of kinetic plus potential, is going, what happened? Kinetic plus potential is going to be this number, because you come from rest. You don't have kinetic at all. You have 0 kinetic. So the only energy that you have is potential. So as you come down, you're going to lose potential and gain kinetic. So by the time you reach this point in here, this is how much potential you're left with, but you gain this much kinetic. In such a way that if I add this 2, I still have the total energy that I started with. So if I start with 10 joules, for example, I have 10 joules. If this happened to be here, I had to be 8 joules, this must be 2 joules. In such a way, the potential energy is 2 joules left, but the kinetic energy now is 8 joules. If you go on the second run in here, you're going up high this point in here, and let's say the potential now increased to 6 joules. Then I know how much kinetic you have. You have 4 joules. So by the time you are in the point below, you have a lot of kinetic energy. But then if you go higher, you're going to lose some of that kinetic energy because you only have 4 left. Half of it is gone because you reached this point. But the potential has increased now. And let's say, for example, this is 1 joule potential. So again, then this whole thing is 9 joules now in terms of kinetic. Let's say, for example, this happened to be 3 joules. Then you guessed it. This must be up to here only, okay? This must be your 7 joules in such a way that always at any given point in here for the roller coaster, the sum of kinetic plus potential is whatever initial value you started with. It's the same thing. It doesn't change. It's always the same. Okay, so this is what we mean by conservation of energy, provided, and this is true, that there are no losses in energy in this case. And there are no pumps of energy also either. In other words, this roller coaster has no friction. Obviously, a real roller coaster will have friction, okay? Despite of all of this oils that they put on the wheels and all of that to make them run smooth, they are still with friction, okay? Friction, first of all, the moving parts between them and the moving parts in them. To compensate for that, and also there is air resistance, and there is sound. Actually, if you have ever been on a roller coaster, you hear all kinds of sounds from the wheels and all kinds of things. So the energy is lost in that form too. So there are losses of energy, but then the entire thing probably is driven by a motor of some sort, the electrical motor or something that is probably driving the whole thing. So in this case, not only there is a change for the worse in terms of energy, it's not just being lost, but also there is a supply of energy coming from the engine. So an engine actually will supply energy to your system. Dissipative forces like, for example, friction and air resistance will take energy from your system. So that's how this problem can be thought of. For example, let me give you another example in here about this conservation of energy. You're here, you live somewhere in here. This is your house on a hill. And this is, you're going back home, okay? So you start, let's say, for example, you're in the grocery store, you just bought your eggs and things like that. So your car is stopped. How much kinetic energy you have? You have 0. It's not moving, okay? You go in the car and you start it and you go all the way up to the hill and park your car in front of your home. And now how much kinetic energy you have? You still have 0. So there is no change in kinetic energy. So the kinetic energy in the beginning and the kinetic energy at the end is 0 because the car stopped. Okay. But then the potential energy, if we take this one as the origin, and again, this is always an important point. You have to always find the reference point for the energy, the potential energy. So let's take the potential energy to be 0 in here. You could take it anywhere you like, because at the end, what matters is the change in the potential energy in the story. But now this has a given potential. So this number is not 0. How do I know? If I brake the car, if I remove the brakes and the car can start sliding, it's going to gain, it's going to lose that potential energy and gain kinetic energy. By the time it reaches this point, it's going to be rolling at a high speed. So in this case, the potential energy is not 0. So what happened to the total energy? Initially, the total mechanical energy between potential and kinetic is 0. At the end, it's not 0 anymore. So where did that excess of energy come? It came from the gasoline that you paid for in the gas station. When you put the gas in the car, and when you started the car, if it's an electrical car, when you charged it actually from the power company, when you're wall, okay? So where is this thing jumping on me? Okay. So the point being in here is that is where that energy is. So the difference in energy, so that potential energy, where it came from the engine, basically firing up and putting more energy into your system. Okay. And it actually put more than that potential energy that you gain. It put some to overcome the friction also. So your engine that you tanked to go uphill is the one that is responsible for that. Say, for example, you don't have a car, you only have a bike. Okay, that's all you can do. Obviously, the incline need to be not as steep. Then where is that energy is coming from then? Okay, I went my bike, got my eggs, and then put them in the basket, and then rode my bike all the way home uphill. I didn't pay for any gas in this case. Well, remember the food that you have, the breakfast you had in the morning before going getting your eggs? That is the one that you have converted, your body converted it into energy, and that muscle energy, which is really chemical energy, that is the one that also changed into potential energy. So as long as the system is closed, and in these two scenarios I described in here, whether with the bike or the car, is not a closed system because it has an engine that is getting energy from external. The kinetic energy in this case, plus the potential energy, is not conserved quantity. It is overall, if you account for the chemical energy that is involved and the friction and everything else, it's still conserved. So energy overall is conserved quantity, no matter how your political affiliations is, whether you're a Green Party person or a non-Green Party person, doesn't matter. It is a conserved quantity. Even in the case that I described in here, provided you have to tally all the forms of energy and how the energy is transforming from one form to the other. In a mechanical system like this one that is isolated, neglecting friction in this case, and sound and all of the other forms of losses, the energy also is conserved. So this is usually in the restricted sense that we talk about in conservation of energy. This one is a more general case. So this is basically in a nutshell what the energy is. The unit for the energy is joule. I mentioned it several times. And the energy for work also is joule, which brings me to another concept in here that is related to this too, to the energy, namely the concept of work. And the concept of work, I already alluded to it in the following fashion. Okay. So it is not. So let's say, for example, let me draw a line in here. This is where the object is moving. This is the floor, for example. Okay, and I have an object in here that I want to move. What I do, I apply a force in here. There are two components to the force. There is a component along the direction of displacement, and there is a component that is perpendicular to the displacement. It is this component that works, not this one. So normal components do not work. No work. Period. They don't do work. Normal to what? To the displacement. Not normal always on the floor. Okay. If I'm moving the object from the ground up, then in this case, that direction is actually the direction of the displacement. The other direction is not. I'm going to give an example quickly about that. So to the displacement, it's important to note that. Let me give a counter example. I have an incline, and I want to take the object from the ground up, okay? Obviously, the object, this is its final displacement. This is how I'm trying to move it. And the force of gravity is acting below. So I have to overcome the force of gravity. So if I want to find how much work is needed, then the displacement is along the force of gravity. So the force of gravity is along this displacement. That is the component that is not normal. This component that is normal to the displacement. So this component doesn't matter. It's not going to contribute to the force because the gravity in here has two displacements, one this one and one normal to it. It is really this along this incline that matters, which is in this case, this distance. So in other words, here is the trick. Let's say, for example, I'll take the object 3 meters high and 10 meters long. And let's say, for example, the object weighs, for example, has a mass, let's say, for example, 100 kilograms. It's a heavy object, 100 kilograms. It's a person, not 160. This thing doesn't meant to be at 100. So I want to know how much work is needed for this object. Well, what matters in this case is this 3 meters high. The fact that you go on a very steep incline or a very lenient incline, it doesn't matter. What matters is the initial and the final points at the end. So what I do in this case, 10, which is the mass, 100, I'm sorry, the mass, times 10 meter per second squared. That is actually, it's 9.8, but I'm making it easy for myself and explaining it by 10. So it's approximately 10, okay, if you wish. If you have time, you just put 9.8. And then multiply it by 3. 3 is the displacement. So again, 100 times 10 is 1,000 times 3, that's 3,000. It's a big object, by the way. 3,000, again, kilogram, meters times meter, that's meter squared per second squared. In honor of Mr. Joule, we gave it a name, joules. Okay? So that's how much work is needed for this case. It doesn't matter. This 10 meter has no bearing whatsoever. That's why it's much easier actually for us, since at the end of the day, you want to get somewhere in the height, to make the incline as not steep as possible. The work is the same. So what differs in this case is the effort. Okay, you have less effort when you go for least steep incline than a very big incline, and you can notice that through the engine that is cracking much more, especially if you're going on a very, very steep, long height. Like, for example, going from California to Arizona on those hills, trying to go up to the plateau, the North American plateaus. So those are some of the things that they actually, there is a big signs on Highway 10 and Highway 40 also warning you about the AC, especially in the summertime. People have the AC running so high and then the engine running so high and the RPM goes so crazy. That's the effort, not the energy. The energy is the same, or the work in this case is the same. So this is an important concept about the energy, about the work. The work, I mean, 1/2 of mv squared is the same also units. 1/2 has units, mass times is kilogram, times velocity squared is meter squared per second squared, that's also joule. MGH also, potential energy is the same thing. This is what I actually, potential energy is too. So this is work for this case, but that's also the potential energy in this case that was gained. Because if I let go of this object, it's going to roll down and it's going to gain velocity. So if I let go of this object 100 meters squared from here and I drop it, how much velocity is going to get? 100 kilogram, I'm sorry. So if I drop 100 kilogram from this height, how much velocity is going to get? Well, at the end, it has a certain velocity. So it's 1/2 of mass times velocity squared. In the beginning, it started from, I'm sorry, it has, let's say, for example, this is the end. So it reaches this point, okay, with the velocity v. Here, it has 0 velocity. So, but it has 0 height at this point. This is the height with which I'm referring to the energy of the origin of the potential energy. So at the end, I have 1/2 of mv squared plus 0 potential energy. In the beginning, I have 0 kinetic energy because it was not moving. 1/2 times 0 squared, that's 0, plus mgh. And mgh in my case, its mass is 100. G is 10 meter per second squared. And the height is 3 meters. So actually, if I multiply this 3, it's going to be 3,000. It's the same thing that I did earlier. So how much velocity is going to gain? 1/2 times m, that's 100 times 1/2, that's 50. Plus times velocity squared. Plus 0, that's 50 times velocity squared, is equal to 0 plus 3,000, that's 3,000. Cancel one of the zeros with this 0, and 300 divided by 50, that's 60. and that is v squared. So take square root of 60, which is roughly 8, 7 point something. Let me check exactly how much that is. Square root of 60. 60 under the square root is 7.75. So velocity then, don't forget you're going to take the square root of this number. So this is velocity squared. So if I take this calculation and carry it in here, so that means the object is going to be moving with 7.75 meter per second when it reaches the ground. So by the time it reaches the ground, 7.75 meters per second. This is a typical homework problem, okay, for this class. So if you have an object that is moving from rest and you drop it, how much kinetic energy is going to gain, how much velocity is going to gain, then you apply conservation of energy and neglecting all kinds of friction, neglecting all kinds of other effects. Then 1/2 of mv squared when it reaches the ground plus 0 potential energy is equal to the kinetic energy when it was dropped from rest. That means its initial velocity is 0. So that means its kinetic energy is 0 plus the potential energy it had. So it converted all of this 3,000 potential energy into kinetic energy. That's basically in a nutshell what that is. All of the 3,000 joules that it had in here has been transformed and became 3,000 joules of purely kinetic energy, 1/2 of mv squared. Then you have the mass divided by 2. In this case, 100 divided by 2 is 50 times v squared is equal to 3,000. And you do the algebra in here, you take the square root and you find how fast the object is moving. So this is how problems can be solved using the work energy theorem or the conservation of energy, actually, in this case, okay? So we still have a little bit of time, so we really need to talk about this example in here because we mentioned it actually when we did the collision. Imagine you're playing billiards, okay? Obviously, you have in this case the 8 ball and the white ball. This is called the cue ball, I think. You hit it with a certain velocity. For the case of the example, I think you gave it what, 4 meters per second. Okay, so this one is moving with 4 meters per second. So I'm not writing the unit in here, but hopefully you guys can fill the gap in here because it's in the example. It's in the book actually. And this billiard ball has a mass of 200 grams or 0.2 kilogram. Again, I'm not writing that one. This one is at rest. 2 possibilities that you might explore. One possibility that the white ball stops at its tracks, provided you don't give it any spin. Remember the point of impact. I don't know if you guys have had a chance to play billiards or not, or pools, that's how it's called in here. The point of impact for the white ball when the stick hits it really matters, because if you put it right where the center of the gravity is, it's going to go slide through. But if you hit it on the bottom, we're going to give it a spin about its own axis. But again, if it's to the right, you're going to give it a spin this way, or to the left, you're going to spin it the other way, or on the top, actually, it's going to spin a little differently. So where you hit the ball matters. The professional pool players, they really know that. They're extremely, and the word actually is used to describe the spin of the ball is called the English. How much English would you give it? Anyway, the point being in here is, provided you don't give it any spin whatsoever, it's not spinning, it goes straight up. So in this case, the ball will stop in its tracks, and the 8 ball now will go with a velocity that the other one had. So this one also is a 0.2 kilogram. Both of them have the same velocity. So in this case, it's easy to compute the momentum initially. So the momentum is this mass times this velocity. So the momentum is 4 times 0.2, which is what? 2 times, it's 0.8 meter per second square, 0.8. Because 4 times 2 is 8, and then you have a decimal point in here, 0.8 kilogram meter per second. So that's how much momentum you had in here. The other one has 0 momentum because it was not moving. This at the end, the white ball has a 0 momentum. This one is the same mass times the same number. So at the end, it's going to be 0.8 kilogram meter per second. So momentum is conserved. There is another possibility though. okay, another outcome, where both of the balls will be moving. And in order to satisfy the conservation of momentum, this one will be moving at 0.4 kilogram meter per second, and there this one also will be 0.4 kilogram meter per second. So when I add up these two, I will find 0.8 kilogram meter per second, which is what I had. So the momentum is conserved in either case. And here you split them equally because they are the two masses are the same, equal mass, and they move together, basically, with the same speed. How do I know it's the same speed? Because the momentum is the same and the mass is the same. So how much speed is going to be? Remember, each momentum is equal to the mass, which is 0.2 times their speed, v. So 0.4 divided by 0.2 is exactly 2. So each mass will move with a velocity that is 2 meters per second, which is half the velocity of the initial cue ball. So in this case, what happened to the kinetic energy? And that is a key critical point in here. The kinetic energy for the black ball in here is 0. So the kinetic energy also is 0. Its momentum is 0 because it was not moving. Easy to find. The kinetic energy for the white ball is 1/2 times its mass, which is 0.2, times the velocity squared. Remember, the velocity is 4. When you square it, it's 16. So 16 times 0.2 divided by 2, I'm sorry, is going to be 1.6. 1.6 joules now, because it's a kilogram meter squared divided by second squared. So in this scenario also, it's going to be the same thing, because this one has no kinetic energy because it stopped. So the white ball now has no kinetic energy. This one is moving with the same velocity as the initial one, which is 4. So in this case, I'm going to do the same numbers in here, which is 1/2 times 0.2, which is its mass, times its velocity squared, and the velocity squared is 4 squared, and it's going to give me the same number, 1.6 joules. No problem. So the kinetic energy is conserved in case B. In case C, it's going to be different. And let's see how much it is. Remember, the initial kinetic energy is 1.6 joules. I'm going to write it in here because I have space in here to write down. So each one will have the same kinetic energy because they are moving with the same speed of 2 meters per second. And they have the same mass. So it's the same 1/2 times 0.2. That's the mass. Times the velocity squared. And the velocity squared now is 2 squared. So 2 squared is 4 times 0.2 divided by 2. That's it's going to be 0.4 joules for each and every one of them. So there are 2 of them. So now I'm going to add up the other one to it, and I'm going to find that 0.8 joules is the total energy, kinetic energy of the system I have. So what's the difference between case B and C? Well, case B conserves kinetic energy. And since they are moving on the floor, they are moving in the same place, they're actually kinetic potential energy also is the same, did not change. So the total energy is the same. So this one, case B, kinetic energy is the same, did not change, conserved. This is what we call, I'm trying to write an E in here. This is what we call elastic collision. This is elastic. I'm assuming everything is ideal, okay? If you did this one at home, if you had a chance to go somewhere in the billiards and play it, and if you hit the ball right in the right place, you're going to produce this one. So the collisions on billiard balls really are elastic collisions. I mean, granted, if you are picky about it and you want to really find the minutia, you're not going to find it exactly the same, but practically it looks the same because there is a friction with the surface of the table and the sound that you hear, clack that you hear, collision, and all kinds of things. Okay, but case C, in this scenario, it's not going to be produced unless something that you had a spin of some sort. Okay, you didn't hit it right. And even then, there is a separation. They're not going to be moving with the same speed. Okay. So Case C, the kinetic energy is not conserved. Not conserved, okay? So in this case, it's an inelastic collision, inelastic. So please read the book, go through these examples, make sure you understand them, especially when it says work it out, try to understand them. If you have any questions about all of these things, please do not hesitate to send me messages because this is part of the requirement for this class. The last topic in here for this chapter is actually the concept of power, okay? I mean, in here we mentioned that the forces that don't work basically are the forces that do not do work. Basically, are the forces that are perpendicular to the displacement. We discussed that when we talked about the different components of the force. The other concept that we want to talk about, this is actually an example of the roller coaster. And as a matter of fact, the example of the roller coaster, which is a textbook example, is everywhere. Okay, here is all. Every day you could do this, so you can talk about this one. So it's really not something original, honestly. Okay. All forms of energy, of course, which is 1/2 times mass times how much the spring is compressed or decompressed squared. So this is other forms of energy also. Let me talk about the concept of this is actually part of the discussion that you guys are going to have in your discussion today. This is the concept of power, okay? And I know this was also part of the lab. So how much energy is changing per unit time is the power. Power is measured in watts, in R of Mr. Watt, okay? And usually the power company uses the kilowatt hour as a way to measure how much energy is consumed. Remember, a kilowatt is 1,000 watts. An hour is 3,600 minutes. So basically, this is 1,000 watts, 3,600 seconds, I'm sorry, times 3,600 seconds. So this is watts of energy, because remember, energy in this case is power times the time. So this is actually a unit of energy. So the kilowatt that is used by your power company to bill you at the end, they usually charge you 14 cents, 17 cents, depending on the location, depending on the power company, and depending also on the time when you're using that. That's how much, that's actually energy, but the watt itself. So let's say, for example, you went to a Walmart or a store, any store for that matter, and you grabbed a 100-watt light bulb, okay, and you turned it on. And you want to know when would you be able to get a kilowatt out of it? Well, kilowatt, you have to let it for 10 times an hour, because it's only 100 watts right now. So basically for 10 hours straight, you're going to pay whatever that rate of the power company is. Let's say, for example, it's 20 cents. You're going to pay 20 cents for it. This is not cheap because you have so many of them at home and you have so many things. Like, for example, a heater, typical heater is about 1,500 watts. It's already 1.5 watts. So if you let it go for 1 hour, that is already 30 cents on it. Okay, so that's how you compute your power usage at home. Okay, if you have, for example, I don't know, TV that goes for 500 watts, then the TV going on for what, 5 hours, no, for 2 hours actually will get you also a kilowatt. Okay, and so on and so forth. So that's really how you compute things that have a lot of wattage, and if they're left on for a long time, they will result in a more power use. But this is really the power. The power is the rate at which energy is being transforming. Is going from one form to the other, or how much work is done also per unit time. That too also is power. Okay. So this is in a nutshell all the stuff related to this topic, to this chapter. And I know I mentioned briefly the concepts that are going to be discussed in the lab. I will try to have this posting as soon as possible, and we will discuss today in the lab in more details about the lab itself, which has to do with electrostatic forces, and we do the lab. Okay, so I'm going to follow up this session with some messages for not necessarily today regarding the exam and other assignments. Thank you, guys.